and tell me what you get here. Okay, so this was the number 11 here. Go on to number 12. Now, if we take copper and silver nitrate, we're going to form copper nitrate and silver metal. But which copper nitrate should we form? Copper 1? What's the other charge of copper? Copper 2. But if you have a choice, let's go with the larger one, which would be copper 2. And so if we have a choice, we're going to go, otherwise we're going to have to write both of them out. Do you want to write both of them out in two equations? No. And so it would be better just to go with the ultimate one, which would be copper 2 nitrate. That's what I suggest. If we did form copper 1, then either we'll just mix it together and not balance it, or we'll have two separate equations. The two separate equations would be one equation forming copper 1 nitrate, the other equation forming copper 2 nitrate. And it depends on how good. Which one is the oxidizer here? Remember I talked about the oxidizer and reducer? Which one is the oxidizer?
The copper.
Actually, the copper I call the reducer. A is the reducer. What was the oxidizer?
The reducer is the one with the electrons.
Yeah, and copper doesn't. Copper's a metal, so it has electrons. And copper is a good conductor of electricity, and you can knock some of those electrons off. Or somebody can take those electrons, like oxygen. When oxygen takes electrons, it turns black like this eventually. Eventually, take time. I mean, it's not to say we can't form copper 1. So who's taking the electrons? Well, actually, the nitrate doesn't change. You see, the nitrate stays the same. And so nitrate is what we call a spectator, because this goes to AX, and AX is the same, X is the same, but A is not the same. It turned out that the silver takes it. The silver takes it because it's not silver metal. What is this? Silver ion, which is plus. Silver ion takes the electrons from copper. And then we form silver metal out over here, Ag. So what's the formula for copper 2 nitrate? CuNO3 2.
Because it's taking away from it.
And so that's what we end up with. And now silver, if it's powerful enough on an oxidizer, then we should oxidize it to copper 2. If it's weak, then maybe we stop at copper 1.
If it asked us what the oxidizer was in this equation, would we say AgNO3 or just Ag?
You could say either. You could say AgNO3 is the oxidizer, or you could say Ag in AgNO3 is the oxidizer. But you wouldn't say Ag like in silver metal. Silver metal would not be an oxidizer. Silver metal is not going to take electrons to form a silver anion. And so, but in this case, nitrate is what we call a spectator. It doesn't do anything. And so the Ag plus is what's taking electrons in this particular reaction. And so this is why we end up with this. We'll talk about nitrate is more complicated than this, but this is the oxidizer here. And the reducer is copper metal. And so to balance this, we'll need how many coppers? 1. How many silver nitrates? 2. And then how many silver? 2. And then that would be balanced. Then we look at solubility. If there's water around, silver nitrate is normally a white solid, but will it dissolve in water? So first we look at the cation. Is that a group 1 or ammonium? No. Then we look at the anion. Nitrates acetates and chlorates are all soluble. So this would be AQ in water. That's not group 1 or ammonium. We look at the anion. All nitrate salts are soluble. So that would be AQ. And then silver is a metal. Do silver coins dissolve in water? No. Do copper coins dissolve in water? No. So those are both solids. Those don't dissolve in water. And so this would be the A plus BX pattern. But these patterns, I mean, these are just a few of the patterns. You know how many patterns you have to memorize? You know, how many different types of chemical reactions are there? If you think just in your body, how many different chemical reactions are happening inside your body right now? 1?
At least.
No, too many. Innumerable, right? A lot. And so, in fact, they don't even know what a lot of these proteins are doing. They don't know what 10% of the proteins are doing in your cell. They have an idea. I mean, that's why they came up with the 10%, because there's got to be something happening in there to do certain functions. But do they have it clearly mapped? And if they had everything clearly mapped out, then it'd be easy. You know, coming up with a cancer drug would be so easy. If they knew everything that was going on in the cell, you know, it'd be easy to come up with a cancer drug. Alzheimer's, you know how many times they've tried to come up with an Alzheimer's drug? Although I heard one of them is pretty promising that's just coming out, but you know, there's a clinical trial that just failed recently. They had high hopes for it, but unfortunately. So it's complicated. Do you think these 3 patterns are going to be enough? No. And so normally in Chem 4, I go through a much more general, broad approach to this, but I thought, you know, that's what I did last semester, but they didn't do so well. And so what I'm going to do is I'm going to do a simpler approach, I think, to this chemical reactions. And so what we're going to do is I'm not going to go into it so heavily like I did. And so the last year's exam, I didn't, because I went so heavy into chemical reactions that I didn't test for it on the midterm. And you might notice, well, this seems a lot different. But this semester, I'm going to try to take it a little easy and a little easier. And so you might have some simpler patterns, you know, on your midterm. These are simpler patterns. Whereas if I showed you the chemical reactions that I gave last semester, it would be a lot more intense as far as predictions go.
Can you give us some sample problems that you thinking about putting on the exam for that, since it's not on a study guide? Or I guess it's just the ones like that.
Yeah, like this. The only difference is I wouldn't give you the formulas, I just give you the name, and then you just write the formula. Yeah. And so you just have to be able to write the formula, and you'll be all right. There's a couple more patterns, though, that I'd like you to know.
Yep, he's gonna give us the names.
This is harder than that.
The couple of more patterns that I'd like you to know. Combustion.
The formula. Imagine you get the first part wrong.
That's gonna happen. That's definitely gonna happen.
So if we take something like CXHY, X and Y are going to be different numbers. These are called hydrocarbons. They're compounds of hydrogen and carbon. And we combust it. What do we form? When we combust it, we'll just burn it in O2 or air, and we're going to form what? Carbon dioxide and water. So we're going to take this all the way to CO2 and H2O liquid. Of course, we can form soot, and we can form carbon monoxide, but you don't. You just take it all the way. This is called complete combustion. When we form soot, And carbon monoxide, that's incomplete combustion. And we don't want to write multiple equations for each product that might be able to form. This is a hydrocarbon. These are different. CXHYOZ. These are like alcohols. It would be ternary like this. Sugars or carbohydrates. There are others, etc. Ethers, aldehydes. Aldehydes? No, not aldehydes. Acids, etc. So when we burn these, it's the same thing. If I burn a hydrocarbon or a hydrogen carbon oxygen containing compound, I'm going to form the same product. So the same products would be CO2 and water. And so it's just an issue of balancing. And so butane C4H10, and let's go ahead and combust butane. So C4H10 plus O2 yields what? So you should be able to predict what it's going to form. What's going to form? CO2 and water. Okay, then we balance this. We save the oxygen for last. So we have 4 carbons here. I need 4 CO2s to give me 4 carbons. And so the carbons are balanced. We have 10 hydrogens here. I'm going to need 5 H2Os. That will give me 10 hydrogens. And then I count the oxygens. I have 8 plus 5 is 13 oxygens. And then I'll go 13 halves O2. That'll give me 13 oxygens there. Now, it depends on how you visualize what's happening here. Butane is normally a liquid. Have you seen butane lighters?
Yes.
Is butane a liquid or a gas? It's a liquid, yeah. And so butane is normally a liquid, but it's what we call a volatile liquid and can easily vaporize into a gas. And so we go from butane liquid to butane gas. O2 is a gas, CO2 is a gas, and H2O is initially a gas, but then it's going to condense into a liquid. Leave that there. Okay, next what? Next, they're asking us to do wall state and all these other things at the particulate level. This makes no sense at the particulate level. At the particulate level would be individual molecules. So if I had 1 molecule of butane, I'd need half a molecule or 6.5 molecules of O2. I can't have half a molecule of O2. So at the particulate level, this equation doesn't work. At the mole level, this does work. If I had 1 mole of butane, which would be 6.022 times 10 to the 23rd molecules, I could have 6.5 moles of O2. And that would be easy. But at the particulate level, we can't have fractions. And therefore, we have to get rid of the fraction, which means we'll double everything. So we'll get 2 butanes, 2 C4H10s, plus 13 O2s. This is going to yield 8 CO2s plus 10 H2O liquids. And so this particular problem, they want you to look at it in terms of ball and stick. In terms of ball and stick, we're not going to do it. We're going to do it in terms of a structure. So butane looks like this. It has a chain of 4 carbon atoms, and there are hydrogens attached to it. Each of these lines refers to a bond, so we have it all bonded together to form a discrete molecule. So this is 1 molecule of butane. In this reaction, we need 2 molecules of butane. 2 molecules of butane is going to give us a total of 8 carbons and 20 hydrogens, if I count up all the hydrogens. And then we have 13 O2s. O2 looks a little different. O2 we usually draw like this. And we're going to have 13 of those for a total of 26 oxygen atoms. So I'll just write etc. here. I don't know why they're making me do on this particular one, because there's so many molecules. Then we're going to have 8 CO2s I don't want to draw out all the CO2s, but the CO2s are going to look like this. Now, this is what we call a double bond. The lines linking these atoms are called bonds. So we have a single bond and double bonds. CO2 has double bonds as well. Okay? And we're going to have 8 CO2s. Here. And so I have 8 carbons here. And each CO2 has 1 carbon, so I'll need 8 of those to balance out the carbon atoms. Atoms can't be created and they can't be destroyed. And so they just are rearranged in a chemical reaction. And then I have 10 H2Os. So it's and so when you draw it out like this, what you're doing is you're trying to track the atoms. So they want ball and stick. So we got these 4 and these 4. That makes 8. And then we have 1, 2, etc. 3, 4, 5, 6, 7, 8. So we can follow those. So this is at the particular level, but at the mole level, we have so many of these. Or just balance of moles. The problem with these, so we have combustion here, the combination. They're telling us what forms here. Decomposition, single replacement, double replacement. And so this would be more like your test here, like number 20. And so let's see if you can do number 20. And then there's some more that we'll look at later. But number 20 is magnesium plus sulfuric acid. There are 3 acids you should never get wrong. You know what those 3 acids are? Hydrochloric acid, sulfuric acid, and nitric acid. Never get those 3 wrong. You know, otherwise. Those are 3 of the most common. There's acetic acid. Acetic acid is very common, but people get that wrong all the time. That one's more forgivable if you get it wrong, acetic acid, because it's harder to remember. But hydrochloric, sulfuric, and nitric should never be done. If you're going to know only 3 acids, know those 3.
I don't know. That's okay.
Sulfuric, hydrochloric, nitric. Guaranteed. You'll have those. Unfortunately, you'll have a bunch of other ones too. If the test only consisted of those 3, it would be a lot easier. Make your life easier.